So in the last part of the trilogy on this chapter, we're going to look at a goodness of fit test. The goodness of fit test essentially allows us to postulate a distribution and check to see whether or not that distribution is manifested by the sample that we've actually taken. All right. So if we have a number of categories, and a very good example of that is to look at the distribution of grades. So if we take from A to F, if I provided a distribution, and I postulate a distribution, say, well, 30% of students get A's, 25% of them get B's, another 25% get C's, 20% get D's, and then 15% gets F, or whatever it is. If it has to add up to 100% though. So that would be my postulated distribution. However, I would take a random sample of students and see how many of them got an A, how many of them got a B, how many of them got a C, how many of them got a D, how many of them got an F. And that would then allow me to test for the goodness of fit. All right. So we have a particular problem that we're going to look at here. And here we go. I'm going to expand it a bit so we can see better. Shareholder scoreboard ratings. The Wall Street Journal's Shareholder Scoreboard tracks the performance of 1,000 major U.S. companies. The performance of each company is rated based on the annual total return, including stock price changes and the reinvestment of dividends. Ratings are assigned by dividing all 1,000 companies into 5 groups from A to E. Shown here are the one-year ratings for a sample of 60 of the largest companies. Do the largest companies differ in their performance from the performance of the 1,000 companies in the shareholder scoreboard? Right? So basically, if you look at the ratios right here, ratings are assigned by dividing all 1,000 companies into 5 categories. Notice A 20%, B 20%, C 20%, D 20%, and E 20%. So all 5 categories are supposed to be 20% of the total number of companies observed. However, we do have a sample that gave us the following information. We have 5 out of 60 companies, 8, 15, 20, 12. As you can see, there seems to be a little difference between those because according to the distribution, it's supposed to be the same for all of them. All right? So out of 60, if each of them are going to get 20%, then out of 60, there should be 12 companies. So very easily, we could calculate our expected values. 60 companies, 20% per category. So therefore, 20% of 60 is 12. 2 6s are 12. So basically, that should be 12. This should be 12. This should be 12, 12, and 12. That's what it should look like if the postulated distribution is true. But as you can see, there's a difference between 5 and 12, 8 and 12, 15 and 12, 20 and 12, and those two are the same. But the question is that difference sufficient enough for us to conclude that the distribution for the companies, right, in the sample differ from what was postulated? All right. So let's look at that question. Again, same idea, but we set our hypotheses. So the fit is a good one. The fit, that the fit is not a good one. Fit is good versus the fit is not good. If the fit is good, then it means that PA is equal to PB is equal to PC is equal to PD equal to PE is equal to 20%. Right? Remember, all 5 categories are 20%. If the numbers were different, I would have to specify what it is for each one of them. But because they're all the same, I could write it like this. And that's HO, sorry. HA is that the proportions differ, right? The proportions differ from the postulated distribution. All right, so there's a difference between the distribution and what we see. That's step one. Step two, test statistic. So the test statistic is basically chi-squared is equal to f minus e squared over e, and we don't really have a matrix, so it's just that. All right, and all we need to do to get the e values, expected values, is to simply multiply the total sample size by 20%. So that's 12. There should be 12 in each category. But from the sample, we can see that we don't have that. Decision rule. So we are going to use a 5%, and then the degrees of freedom is just k minus 1. All right, and so we have 5 minus 1 equal to 4. So our critical value, chi-squared crit, is chi-squared 0.05, 4 degrees of freedom. Let's see what that is. Four degrees of freedom, 0.05, 9.488. So if chi-squared observed is greater than or equal to 9.488, we will reject the null hypothesis. Otherwise, fail to reject the null hypothesis. All right? Good. So, step 4, analysis. Now remember, I've already shown you that we have the expected values right here. And these are your observed values, your F's, and these are your expected values. So in essence, all we need to do is to get chi-squared is to say 5 minus 12 squared over 12 plus 8 minus 12 squared over 12 plus 15 minus 12 squared over 12 plus 20 minus 12 squared over 12 plus, that should be 0, 12 minus 12 squared over 12. Okay, so that's how we would actually get chi-squared right away. We don't need a bunch of calculations to calculate the expected frequency, since it's fairly straightforward. 20%, all right? 20% of each in each category. So when we distribute the 20% in each category, that's what we would get. Now, let us figure out what the chi-squared value is. It turns out that chi-squared is 11.5. 11.50, which is greater than the 9.418. And so therefore, we will reject the null hypothesis. But let's find the p-value. So let's do 2. So we have, from what I showed you, chi-squared is equal to 11.50. The p-value is the probability of chi-squared greater than or equal to 11.50. When I look at the table, what do I get? Look at the 4 degrees of freedom, and I am looking for 11.5. That 11.5 is between 0.025 and 0.01. 0.025 and 0.01. So the p-value between greater than 0.025, sorry, less than 0.025, but greater than 0.01. All right, there we go. And so therefore, step 5, our decision conclusion. 5, decision conclusion. Since 11.5 is greater than 9.488, reject the null hypothesis, and that the fit is not good. Essentially, the largest companies differ in performance. That's our conclusion. The fit is not good. That is, the largest companies differ in performance, because the suggestion was that we had 20-20-20-20, but among larger companies we don't see exactly that same distribution. We see something different. Again, in this example, possibility of type 1 error. All right, possibility of type 1 error. Risk of type 1 error is between, as you can see here, it's in between 0.025, 0.01 and 0.025. Okay, so that, folks, is the goodness of fit test. So I've just completed the 3rd installment in looking at the 3 things: equality of proportions, test of independence, and goodness of fit test. I don't believe there's another part to this question, but let me just double check. Nope, that's it. So it's fairly straightforward in terms of what we're trying to accomplish. All right, so that brings us to the end. All of these formulas are fairly similar in terms of F minus E squared over E. Row total times column total over grand total will give us the expected values. And even in the last case, a row total, column total can be used, except that all we have is a single row. So we could just kind of, by inspection, figure out what the actual probabilities are supposed to be. All right. Okay. Hope that was helpful. Take care. Thank you.